In the 1950s, the academic and mathematical consensus was absolute. The casino cannot be beaten. Even legends like Henri Poincaré argued that predicting roulette was impossible due to inherent randomness, or what physicists call noise, the unpredictable microscopic irregularities in a physical system. But at UCLA, a young physics graduate student named Edward O. Thorp sat with his peers and casually stated that Poincaré was wrong. The house could be beaten. Thorp's internal operating system was simple. He refused to accept expert authority without first conducting an empirical test himself. The casino industry possessed immense wealth and power, but a penniless student with an empirical mindset was exactly what was needed to hack the world's most robust systems. Thorp's approach started during the Great Depression in Chicago. His childhood experiences forged two lifelong rules: never blindly trust adults, and always test the limits of your environment. When warned that a stove would burn him, he touched it to verify the claim. When told fresh eggs crack easily, he squeezed one slowly, applying escalating pressure to pinpoint the exact microsecond its structural integrity failed. As a teenager, he scaled these physical tests into applied theoretical math. He designed experiments to manipulate massive public spaces, culminating in a prank at the local Long Beach plunge. This diagram illustrates the indoor pool, which held roughly 1,000 cubic meters of water. Thorp calculated that aniline red dye had an extreme coloring ratio. A single gram of this chemical, dropped into the water, geometrically multiplied and turned the entire volume blood red. Thorp used these moments to verify a broader theory. Calculating the underlying math of a system allows for the total manipulation of massive real-world environments. Thorp encountered his first rigid elite academic hierarchy during a regional high school chemistry exam. He understood the theoretical math but lost to privileged students with superior mechanical tools to calculate answers before time ran out. Thorp adapted. He mastered a slide rule and returned the next year to dominate the physics exam. The lesson he carried to Wall Street and Las Vegas was clear: raw intelligence is insufficient. To beat a system, you must acquire and master the exact mechanical tools that govern its rules. Back at the UCLA tea table, Thorp mentally stripped away the flashing lights and the glamour of the casino floor. He focused on the heavy, mechanical reality of the game. This schematic shows Thorp's core breakthrough. The roulette wheel is not a magic generator of chance. It operates as a simple model of planetary orbit, where the ball is a mass subject to measurable friction and gravity. By timing the speed of the rotor and the ball, Thorp could calculate the decaying orbit. He could predict the exact quadrant where the ball would land, cutting straight through Poincaré's theoretical noise. Reframing a feared game of chance as a problem of classical mechanics allows an unbeatable system to be treated as a machine waiting to be reverse-engineered. The mathematician Nassim Nicholas Taleb noted a striking contrast in Thorp's career. While other mathematical geniuses went bankrupt, Thorp became a billionaire godfather of quantitative finance. Quantitative finance is the use of mathematical models and large data sets to analyze financial markets and securities. Academic finance often builds fragile, hyper-complex theories. Thorp instead relied on radical simplicity, identifying a clear, obvious edge and precisely dosing his bets to eliminate the possibility of ruin. Thorp's success did not come from an ability to predict the future. He realized the world is a laboratory. If you reject the experts, simplify the variables, and conduct your own tests, you can find an edge anywhere.